perform some mathematical operation, which means addition, subtraction, multiplication, integration, differentiation, weighted sum of many mathematical operations you can perform. Now you provide input. When you provide input to the inverting terminal, this is your inverting terminal. This is the inverting terminal because this is negative, this is inverting terminal. This is inverting terminal. By the way, I updated my slides and posted the latest version before coming to this class. So this is positive terminal and this is called non-inverting terminal. Non-inverting. When input is applied to non-inverting terminal, output you get is the opposite of the input, opposite sign. That is the reason it is called inverting operational amplifier, which means that the output is going to be negative of some gain. It's called voltage gain. Overall gain, GV, voltage gain times the input. So you have some gain. Actually, in the derivation, you will see GV includes negative sign. You will see in a moment. So this is the voltage gain. This is voltage gain. So the output is going to be opposite sign of the input with some scaling factor, and we want to find what is that. So for that, what I have here, if you go to the next slide, you see I annotated the circuit. So you have the input. Input is connected to a resistance R1, okay? And current flowing through this I1 is, the current flowing through this R1 is I1. And this is the inverting input, and this is the non-inverting input. You will have zero current flowing through inverting input, because ideally this operational amplifier will have input impedance, Cin input impedance is infinity. What's that noise?
It's coming from the server rack. Actually using our rack.
Oh, okay. Still bothering, right? Okay.
It's in my head.
Yeah. No, it's bothering me. Yeah, right. Don't cause anything out of input. Okay, so we have that input impedance is infinity. Okay, if you have resistance infinity, how much current will flow through that resistance? If the resistance is infinity, how much current will flow through that resistance? Zero, right? No, its resistance is infinity. So therefore zero current will flow, which means that current flowing through this terminal is going to be 0 ampere, and current flowing through this terminal is going to be 0 ampere as well. Now, so this gain, ideally this gain is infinity, but some voltage from the output will be fed back to the input, and they will oppose each other so that the voltage difference between those two terminals is zero, which means that the voltage difference between these two terminals, Vi equals Vi2 minus Vi1. Vi2, this is Vi2 minus Vi1 is going to be, this is your Vi, this difference is going to be zero. Which means if the voltage difference between these two terminals is zero, guys, what is the voltage difference between a piece of wire? So this is VA, this is VB, and VAB equals VA minus VB. You see, current is going to be zero. So if you have a piece of wire, what is the voltage difference between 2 points in a wire? Zero. So therefore, this voltage difference, ideally, this voltage difference is going to be zero. So you can think of these two connections virtually short. They are not physically connected, but virtually they are connected and they are short. We call it virtually short. Okay? These two terminals are virtually short, which means these two terminals, ideally, they are connected. Okay? Ideally, these two terminals are connected. If these two terminals are connected, which means that their voltage difference is zero. And because ideally input impedance is infinity, current flowing through this terminal is zero, current flowing through this terminal is zero. So no current will flow. Now my question to you guys, look, if we have some voltage source, okay, and voltage source is connected to this resistance, current flowing through this resistance is going to be I1. Now, don't you think, guys, there is, you can think simply, apply KVL here, and this circuit, this part of the circuit is simply one. This part of the circuit is simply, you have VI, R, and then it's connected, this is a piece of wire, and then ground. Don't you think that we have one source, one resistance, right? It's a closed circuit. So what will be the current flowing through this I1? Using Ohm's law, VI over R1, which is simply R1. So we now know what is the current flowing through this R1. Now you have a node right here. And you know that 0 ampere current flows through this terminal. So you have current flowing through R1, it is I1. And at this point, you can apply KCL, Kirchhoff's current law. So zero current flow. Don't you think that this current will simply flow this way? Because you have I1 current flowing through R1, zero current flowing here. So therefore, all this current will flow through this R2. So this is R2 plus.
I1 equal I here.
Yes, that is the goal. So in that case, I1 is simply I2. Okay? That's how we are treating this as a black box. So that's how op-amp works. Ideally, that these two terminals, you can just think of this as a piece of wire virtually ground, and no current will flow through these two terminals. So therefore, all current flowing through R1 will be flowing through R2. Okay, so I1 is simply I2. Now, because of the characteristics of this op-amp, you will have some voltage, output voltage, which is going to be scaled version of the input. Now, don't you think that we can? I'm going to use another color. Don't you think that we can apply KVL right here. Apply KVL here. So you can just think of this as a voltage source here, V naught, and then you have R2, I2. So because current direction I get this way, so therefore positive and negative here. So this is going to be V2. And then here, it's coming right here. And these two terminals are virtually connected. And there you have simply ground here. So you can think of this load as this circuit. So if you think of this circuit as, if you think of this load as this circuit, guys, look, I'm going to apply KVL here. I go here, I see negative V naught. Okay? I see negative V naught. And then here I see negative V2 is I2 R2. So R2 times I2 equals 0, because this is a piece of wire, this is 0. So here you see that V naught is simply negative R2, and I2 equals I1, and I1 equals VI over R1. So which is basically negative R2 over R1 times VI. So we are able to write the relationship between output voltage and input voltage. Did you guys understand? You understood? Okay. So we found the relationship between input and output. Now nicely, what I did, I drew this circuit here. And here I showed the steps that you need to follow to analyze this circuit in circle. So this is step 1, where you assume that these two terminals are virtually short, therefore voltage difference between these two terminals is 0. And then number 2, you assume that this is virtually ground, so therefore I sub I1 is going to be 0. Okay, so this is going to be 0. This is going to be 0. And number 3, you find I sub 1. So I sub 1, we found I sub 1 is P sub I over R1. Number 3, we did that. And then number 4, we assume that here this current is going, current flowing through this inverting terminal is 0. Now number 5, you say that I2 equals I1. So number 5, I2 equals I1. And number 6, you apply KVL. Number 6, you apply KVL. So once you go through all these steps, and I actually wrote it down, these steps. I don't want to go through this. I just simply don't want to write it down. I actually wrote these steps. Okay? So I actually wrote these steps. Again, in the scribing, guys, you simply try to understand and copy these steps. Basically copy these steps and you write it down. This will help you. This will click your brain. Okay? So make sure you write all these steps. And finally, you get the voltage gain from this expression. Output voltage equals negative R2 over R1 times VI, and V out over VI, this is the definition of overall voltage gain, is going to be negative R2 over R1. So do you see that this output is going to be negative of the input, which means that if the input is plus 5 volt, output is going to be negative some scaling factor times the input. You understand? negative scaling factor, which is determined by R2 over R1 times the input. So if your input is sinusoidal signal like that, and let's say R2 equals R1. So if this is input Vi, so the output is going to be V out. So it is going positive here, it's going to come here negative. See that? So output will be like this. So bad at drawing actually. Yeah, that's why I use computer too. So I write program actually to draw signals. So if the input is a pure sinusoidal signal like that, okay, and I said that R2 equals R1, output is going to look like this. Now we have next example. It's a bit complex example. In the previous example, we have only R1 and R2, scaling factor R1 and R2. We do not have control over the input impedance. Now you can actually control somewhat the input impedance with by adding some resistor network. In the output circuit, you can have some resistor network. Now look guys, it might be confusing. In the book, you don't see this circuit diagram. In the book, author has labeled, original circuit would look like this. But in the book, author has labeled the original circuit with all the current directions already. But I actually repeated, I don't have space problem. I actually repeated this circuit. So this is your original circuit. And then, when I solve this circuit, I'm going to redraw and write down all the steps that I'm going to follow. Okay? So this is the diagram that you'll see in the textbook will look like this. But I have a bit difference here because author has put 8 steps, I put 7 steps. So in 7 steps, we should be able to complete. Guys, make sure you understand this circuit analysis. Okay, I'll go through all the steps in a moment. Make sure you understand. Please pay attention. Original circuit, in the exam, I am going to give you original circuit like this, with no labels. Okay? Because when you build the circuit, when you build the circuit, you just see the components, right? In a PCB, you see all the electronic components, but you don't see the current direction and so on. You see input, output, sometimes inputs are denoted with VI, output Vout, V0. These are denoted, but you don't see the current direction here. Current is going this way. But when you analyze, that time you give, for analysis purpose, you provide current direction the way I will be giving right now. So let's see what this example is about. In this example, guys, you see, assuming an op-amp to be ideal. This op-amp ideal, immediately, what you see that this current is going to be 0. I1 is going to be 0 ampere. This current is going to be 0 ampere as well. Immediately, you see that no currents are flowing through each of these terminals. Immediately, because I said that this op-amp is ideal. Because this op-amp is ideal, immediately you know that impedance between these two terminals. You guys know what is impedance, right? By now, a quiz. Actually, you saw this in EC 214 ago, right? AC circuit, you guys know what is impedance, right? What is the unit of impedance? Ohms. What is the unit of resistance?
Ohms.
What is the unit of inductance? And capacitance current. So make sure when you have inductive reactance has the unit ohm, but many people get this confusing. So they write unit Henry. Reactance, unit of reactance is Henry. Yeah, unit of reactance is ohm. Unit of impedance is ohm. So the impedance between these two terminals is infinity. Therefore, no current flowing, and because we have this feedback, because feedback is present, therefore some part of this output will come here and oppose each other. So therefore, the voltage difference between these two terminals is going to be zero. So you can just think of these two lines virtually short. And I actually labeled this because I said that this op-amp is ideal. Okay? Immediately you know that. And because you know that this is virtually short, so you can think of this circuit, a series circuit with one voltage source, one resistance, and this is virtually ground. Virtually, these two terminals are virtually short, and this terminal is connected to ground, so this terminal is basically virtually ground. Okay? So therefore, immediately you know that the current flowing through this R1 is going to be I1. That's how I denote. Current flowing through this R1 is I1. So therefore, I1 is simply VI over R1. Now, because there is a node right here, you can apply KCL, Kirchhoff's current law, and you see that no current is flowing this way. But you know that current I1 is coming this way. Because no current is flowing this way, so all this current will go in this direction. Therefore, if I denote the current flowing through this I2, then I2 is going to be simply I1, which is simply VI over R1. Okay? So we now know what is I2. Therefore, we know what is the voltage across R2. So if I know I2, the voltage across R2, what is the voltage across R2, guys? If I know I2 already, VI over R1. What is the voltage across R2? What is the expression for voltage across R2? I already know I2, which is I1, which is VI over R1. What is the expression of the voltage across R2? I2 times R2. And I2 equals VI over R1. It is going to be VI R2 over R1. Right? So the voltage, if I write down the voltage V2 is going to be I2 R2, which is going to be R2 over R1 times VI. You understand? Okay. I am going to denote, it is me who is actually giving this reference direction. But if the current will flow in this direction, it is not guaranteed. It is not guaranteed that the current will flow in this direction. For analysis purpose, I'm just giving this direction. But when you actually calculate the numbers, that time you will see whether the polarity of this voltage, positive here, negative here, or positive here, negative here. When you actually see the polarity, if V2 is, let's say, negative, In that case, the polarity, actual polarity, positive and negative. Okay? But for analysis, I am giving this reference direction. Now, let's say another reference direction is, and I'm giving the current flowing through this R3 is I3. So because I'm providing current direction this way, I am just going to give positive here, negative here. And the voltage across R3 is, current is going this way, from this point to this point, which means the voltage difference has to be from here to here. So the voltage difference, voltage across R3 is I3. The voltage across R3 is V3. So which is going to be V3 is going to be I3 R3. Let's say I am also going to give current direction for R4 is I4. Current direction I'm providing here is I4, which means current flowing through resistance R4, which means that the voltage difference is V4 this way, positive here, negative here. Okay? And I have another voltage source here, which I can treat as a voltage source because output resistance, output impedance of an ideal op-amp is 0. Now look. So I have labeled everything. As soon as I see ideal op-amp, I label this. Derive an expression for the closed loop gain, which means that closed loop gain GB, overall closed loop gain GB equals V0 over Vi equals what? I need to find V0 over Vi equals what for this circuit. How to pursue this? Okay, and after you do that, use this circuit to design an inverting amplifier with gain of 100, which means that I want GB to be negative 100. I want GB to be negative 100. Negative why? Because it's an inverting amplifier. So the output is going to be inverse of opposite sign of the input. And what is limited here, the input resistance R1 cannot be more than 1 megaohm. Input resistance R1 is 1 megaohm. Assume that for practical reasons, it is required not to use resistors greater than 1 megaohm. So you are not allowed to use any resistors more than 1 megaohm for practical reasons. In that case, compare your design with that base on the inverting configuration of figure 1, which means figure 1 I refer to this figure. This is also inverting configuration. But here I have inverting configuration with output as a resistor. So first, let's find how to find this overall voltage gain, which is V0 over V. V0 is the output and Vi is the input. Let's see how to do that. So I have actually redrawn this circuit, and this is what you will see author has provided. Author did not provide this clean circuit, author has provided this circuit. So, and the difference between my circuit and the author's one is that in author's circuit there are 8 steps, but in my circuit I have 7 steps. Okay? So, and I'm going to find the overall voltage gain, GB. Okay. Step 1. We know that it's already done. Step 1 is done, right? Solution. Step 1. you have virtually short terminals. And in the exam, if you write this test, you don't have to write virtually short. You can simply write 0 volt. Okay. And then step 2, because it is virtually short, this is ground, so this terminal basically you can think of this as a piece of wire. So step 2, you find I1 is simply VI over R1. Step 3, I1 equals I2 equals 0. Zero current is flowing through these terminals. So this is step 3. Step 4, I1 is basically going, all this current is basically going this way, right? So step 4, what is I2, guys?
VI over R1.
I2 is going to be V2 over R2, right? V2 over R2, and basically I2 equals I1, right? I1, which is actually might be confused because we do not know V2 here, because we know I2, so you can simply write I2 equals I1, which is VI over R1, right? So from there, if I ask you what is the voltage across R2, you can simply write V2 equals I2 R2, which is R2 over R1 times VI, right? Okay, so I already did step 4. Step 5, I want to find I3. Guys, look, please pay attention. This is the voltage across V3, R3 is V3. Now, if I apply KVL right here, don't you think that I can apply KVL in this code? Right? So, step 5. KVL in loop containing R3, R2, and op-amp input terminals. Okay, if I apply KVL, guys, give me the KVL equation. What is KVL equation? What is KVL equation? KVL, Kirchhoff's voltage drop. Algebraic sum of all the voltage drops in a closed loop is 0, right? Algebraic sum of all the voltage drops in a closed loop is 0. So closed loop, I'm saying that I started with ground here and I see ground here, right? So if I go, do you see positive here? You can write positive V3. V3, and then you come this way, and you see what is the voltage here? V2, right? And you see negative here, so therefore it is negative. Negative V2. And then you come right here, you see 0 here, right? So we don't have to write 0. So V3 equals V2 equals 0. So therefore, don't you think that V3 is simply V2? And we know what is V2, right? What is V2? We just found. R2 over R1 times V sub I, right? Okay. Now, don't you think that we now know what is I3, which is V3 over R3. So I3 here, current flowing through this resistance is the voltage across this resistor divided by the resistance using Ohm's law, right? So which is V3 over R3, and we did find V3. So V3 is R2 over R1. So you can simply write R2 over R1 R3 times Vi. Am I correct?
That's what I got.
You got it? Okay. So we now found I3, we found I2. Okay, so if you number 6, step 6. Step 6. At this node, don't you guys see you can apply KCL here, Kirchhoff's current law. Kirchhoff's current law says that algebraic sum of all the currents entering into a node. Algebraic sum of all the currents entering into a node is 0, right? So if the incoming currents are positive, I see positive, outgoing currents are negative, so algebraic sum is going to be I2 plus I3 minus I4 equals 0, right? I2 plus I3 minus I4 equals 0. In other words, I2 plus I3 equals I4. So these two currents are entering, and you see the total current I4 is leaving. So in that case, you can simply write I4 is simply I2 plus I3. What is I2, guys? Yeah, V2 over R2, and we did find I2 is simply I1, right? So I1 was Vi over R1, right? And I3, we found R2 Vi over R1, R3. Right? Now, if I want to know what is the voltage across R4, which is V4, V4 is simply I4 times R4, and I4 is I4 times R4. So R4 and I4 we have this expression, Vi over R1 plus R2 over R1 R3 times Vi. So this is my V4.
When you factor the VI out.
Yes. And that's the purpose. We'll have Vi out, factored out. Okay? As he said, let's do that. So R4 over R4 times 1 over R1 plus R2 over R1 R3, and in fact you just put the this up I right here. Are you guys able to see? I'm sorry. You guys okay? You can see, right? Okay. Now the final step. The final step is number 7. Don't you think that I can apply KVL right here? If I apply KVL, what do you see here? Negative V0, negative V4, negative V3 equals 0. Right? So I'm just going to rewrite here formally, nicely. So write step number 7. Apply, you just write it down, apply KVL in loop containing what? V naught,
Three, four.
yeah, you can say R4, R3. These are actual components, right? So apply KVL in loop containing V0, R4, R3. What do you guys see? Negative V0, negative V4, negative V3 equals 0. So therefore, V0 is simply negative V4, negative V3. Now, guys, can you tell me what is V4? Negative V4, what is V4? It's R4 times 1 over R1, right? You can just let me put R4 inside. So R4 over R1 plus, what is this?
R2 over R1 over R3.
So R2, R4 over R1, R3 times VI, right? Minus, what was V3? V3, R2 over R1 times VI, right? So V3 was how much? R2, R1 times V sub R. Now, so let's write this term first. So bring this negative sign out of the way, and you see, you can factor out V sub I, so you can actually write V sub I towards the end. So what you can see here, you have R2 over R1 plus R2 over R1 plus R4 over R1 plus R2, R4 over R1, R3 times VI. Do you see? Now, yes.
I think you dropped the negative. Isn't the R2, R1 term, isn't that negative?
So R2, R1 is negative.
Yeah.
I took this negative
Oh,
out of the way. All these two negatives I took out of the way. So therefore, all these components are put.
Oh, wait, oh, I see this one.
Okay? So now, what you can do, you can simplify, make it pretty. So we can bring R2 over R1 out of the way, and then this guy is going to be 1 plus R2 over R1. I want R4 over R1. So therefore, you can keep R4 there right here, and you can keep R4 right here and R2 right here. So if you multiply, R2 disappear, R4 over R1. So you get this part. And then you took R2 over R1 out of the way, and this was R2, right? R2, R4 over R1, R3. So R2, R1 you took out of this way, factored out. So therefore you are left with R4 over R3. So V sub I. So therefore, V0 over V sub I is simply negative R2 over R1 times 1 plus R4 over R2 plus R4 over R3. You can make it nice, actually. GV equals this. V naught over VI equals this. So you can have this nice box. So this is the final answer for the first part. For the second part, guys, for the second part, I want gain, inverting amplifier gain of 100, which means we want GV to be negative 100. Given R1 equals 1 mega ohm and no resistance greater than 1 mega ohm. No resistance greater than 1 mega ohm. So you cannot choose any resistance greater than 1 mega ohm. Guys, tell me. So I want this part to be 100, right? I want this part to be 100. And in the problem it said that R1 is 1 mega ohm. Let's keep this factor 1. So choose R2 to be 1 mega ohm. Choose R2 equals 1 mega ohm. Okay, so this is 1. In that case, you have 1 plus, you chose R2 to be 1 mega ohm, and let's choose R1 to be maximum. This factor maximum can be 1. Okay, you cannot choose more than 1 mega ohm. So maximum you can get this term to be 1. So you already chose R2 1 mega ohm. So let's maximize this term to be 1. So for it to have 1, for it to give us 1, in that case, we chose R2 equals 1 mega ohm and R4 equals 1 mega ohm. So in that case, this is 1, this part is 1, 1 plus 1 is 2, then this part has to be 98, right? Right? This part has to be 98 if the gain is 100. If the gain is 100, this part has to be 98. So, which is R4 over R3 equals 98. Guys, you now solve for R3. Can you give me some numbers, guys? R4 is 1 mega, which is 10 to the 6 over 98. How much is it, guys? Is it
10,204.
10,000?
10,204.
Okay. Ohm. So which is approximately 10.2 kilo. So your R3 equals 10.2 kilo. So if you chose R1, therefore if R1 equals R2 equals R4 equals 1 mega ohm. And R3 equals 10.2 kilo ohm. This will give us then GB is going to be negative, approximately negative 1 with this parameter. Clear? Mr. Clear? You guys understood how to analyze open circuit? Now next circuits will be piece of cake. So now let's go through. Is that okay? So here design and comparison, I already solved it. Weighted sum, another open circuit. Okay. So we just need to find what is output as a function of V1, V2, dot. We are going to assume this op-amp is ideal. If this op-amp is ideal, no current is flowing through this terminal and no current is flowing through this terminal. These two terminals, voltage difference between these two terminals would be 0. If the voltage difference between these two terminals is 0, which means that this is virtually short. Now we have inputs V1, V2, V sub n. Okay, and current flowing through R1 is I1, current flowing through this I2 is R2, current flowing through this RF is I sub n. So this is basically the summing junction, and it is going to add. That's why it is called summer. So we can actually design an weighted summer, in other words, using op-amp. So in this node, don't you see that I equals I1? This I is going to be I1 plus I2 plus plus I sub n. Don't you see it, guys? You can apply KCL at this node, and you see that this current is going to be the sum of all the individual currents. Okay? Now this current will simply, because zero current will flow through this way, so therefore this entire current will go in this direction. So therefore current flowing through this RF, I sub n, is going to be simply I. Now you can actually get the expression for I in terms of input voltage. So what is the current flowing through this R1? What is the expression, guys? You see that this is one voltage source. You go all the way. So it is simply V1 over R1. So it is simply V1 over R1 plus V2 over R2 plus plus Vn over R1. Do you see that? So we got I, and this is exactly same as I. So we got the expression for I. Now you apply KVL in the output loop. So you apply KVL in this loop. So if you apply KVL in this loop, you see that negative V0 equals, so current direction I get this here, so this is negative, this is positive. So it is going to be, this is negative, this is positive. It is going to be negative of voltage across RF, which is IF, RF. And this is 0, so this is going to be 0. So in that case, V naught is going to be negative IF, or you can write RF first, plus something. Now you can write negative RF times IF is simply whatever you write right here. I'm going to use go color and you put it like. You put it right here. So this is the expression. Now you can actually see that output voltage is going to be sum of input voltage with some weights, and I wrote the final answer right here. So the output voltage is going to be RF over R1 times V1 plus RF over R2 times V2 plus dotted RF over R1 times V7. Don't you think that it is basically adding this weighted summary, adding all these inputs with some weights? Do you see that? V1 is weighted by RF over R1, V2 is weighted by RF over R2, dotted Vn is weighted by RF over Rn. You see that, guys? Because the output is actually sum of all the inputs weighted by this resistance, that is the result. It is called weighted sum. So this circuit is called weighted sum. This circuit is called weighted sum. So I gave some exercise. Please include this exercise in your scribing. Exercise 2.7 and exercise 2.7 and 2.7. Whatever I have in my slide, whatever annotation I have, plus these two exercises would be in your slide. Here? Any question, guys? No? You guys understood? All right. So I will see you on Thursday in that 40 to 61, our junior lab. Thank you. Oh.